Good afternoon, ladies and gentlemen. We meet again. My name is Chiravachradej. Today we'll discuss the stress and deformation of a material subjected to axial load alone. Then let's look at what we have to go through to study this topic. Okay, we'll talk about you need the background. What is needed to be so that we can understand and we can calculate what follow after the axial force is acting on a material. Then how we formulate the whole stress-strain relationship into the force and deformation. Then we'll see example on how we employ those equations, those formulas we derive in the second step. Then there will be some certain reading to be assigned again. Then before we could understand fully what we are doing today, we need to be able to calculate axial force. Basically, you need to understand what axial force is well enough up to the point where you can calculate for application. We have gone through this in statics, or what we call engineering mechanics 1. Then you have to understand the stress-strain relationship via maybe the stress-strain diagram that is in the first video plus the reading you have been assigned to do. Then we also need the knowledge of the stress-strain diagram, as I said. Now let's talk about a piece of material. Okay, this could be a column, this could be a beam, could be anything, just a piece of material. In this case, we don't even fix the cross-section area of the member. Let's say that this material is subjected to different type of forces. There will be 2 point loads at the end, pulling them apart, and along the material there will be some kind of distributed force, but this time not 90 degrees to the member as we usually familiar with. This one is along, meaning it's distributed in the axial force way. And of course, once they are pulled this way, no matter how we feel about it, it will be extending, it becomes longer. Okay? Then that measurement of the length that has changed, as we did last time, we were calling it delta down here. L is the original length before it was pulled. Then of course the task is what happens if we want to know this delta. Okay. Well, since there's changes all the way through, then we tend to find the change inside a small element first, small material first, and then if we can understand the change in that small piece of material, then we can extend it to the whole length. Okay, so we look at the free body diagram of that small piece that we cut at the position of x, any x. The original length of that yellow then becomes just dx, as indicated here. This is the original length of that yellow piece. And the change in length this time is not the total delta. The total delta is the total change in length of the big piece. The small change happens in the small piece, then we call the small delta the delta. Of course, if we calculate, and we should be able to calculate in the real case, the axial force acting on this small element, then we can go further then. Starting by solving what is this little delta, this little change in length, then we combine all these little change in length, then we should get the total change in the length of the material. Then let's move that one to the left hand side of the monitor. There, the small piece. The same picture moving from the right hand side to the left hand side, that's all. The axial stress we discussed before, nothing more than the symbol sigma, and the calculation is the axial force divided by the area. Since the area, as we see in the first picture there will be changing from the first point to the end point, meaning the cross-section area is also a function of x, not a constant. Okay, so I dictated with a in bracket x to dictate that it is, to indicate that it is a function of x. The axial strain, the engineering axial strain we discussed last time as well, it is about the change in length divided by original length. The change in length of this small element is d delta, that d delta. The original length is dx, that dx. Okay, so that's it. One of the assigned reading is the Hooke's law. The Hooke's law defines the relationship between the stress and strain in the elastic region. That is a straight line function with a slope of what we call the Young modulus, or the modulus of elasticity. The symbol is usually capital E, that one. Okay? If you haven't read it up now. Then, of course, because the stress equal to the axial force divided by the area, and the strain equal to the change in length divided by original length, substitute for stress and substitute for strain, that become the expression we look at for this small piece of specimen, this small piece of the material. Okay. Now, as I said, actually what we want to know in this case, we actually know N, the axial force, we can calculate using static. We can calculate area. Well, if we know the geometry, we can calculate rectangles, triangle, circle, we can calculate. So in this, the E, the Young modulus, is from the experiment, material property. Then what we actually want to know is the change in the length delta. In this case, the small change for the small element, the d delta. So we switch the equation or the variable around so that our equation answer our question. Our question is how we determine the change in length. Therefore, on the left hand side will be about change in length. The right hand side will be the equation that we use to solve it. But this is a small change of the small material. Okay? So if we want the whole length L, what do? We sum every single d delta of a small element until we reach one end to the other. In mathematical term, it's integration. So that will be the general form how we calculate the change in length of any kind of material subjected to axial forces. Now, but in general, when we look around, we realize most of the time, I have to say most of the time, not all the time, but most of the time, in one member, say column, say beam, say floor, usually we have only one cross section throughout the beam, one cross section throughout the beam. We have one material or one combination of material, and we also have, well, certain lengths. Therefore, in general, in certain cases, in most cases, we can say that N could be constant or assumed to be quite constant. We discuss about it later in the higher subjects. The cross-section area can be and mostly constant. And of course, the Young modulus, if you don't change the material, the E is the same. Then that integration change into this form. Since N is constant, we can take it out of the integration. A constant out, E constant out, only integration of dx 0 to L end up with L. Therefore, this will be our general expression. Not a general expression, this is a specific expression when axial force is a constant and cross-section area is a constant. And only one material, of course. So, that is the form of the equation we have. Now, let's look at the equation. Okay? Let's say we have a piece of material, just to make it a little bit thinking. Okay? This piece of material from A, B, C. Okay? Two parts. A, B, and B, C, basically. Okay? From A to B, cross-section type was shown. B to C, different cross-section area, and also shown. Okay? There are three forces acting on this. There are 5 meganewton and 2 5 meganewtons acting at point C, pushing it toward at point B, pushing it toward point A. and only one force at point C, 4 meganewton pulling it away from point A. A is fixed, right? A is supported by a fixed support, meaning it doesn't move. Okay, again, this is in static. It doesn't move, it doesn't go up, it doesn't go down, it doesn't rotate. It stays there. Okay, now, the question is this. We want to know what is the stress in AB and what is the stress in BC. Both parts mean both parts. Okay, and we also want to know the movement of point B and point C. Okay, apparently in this case they said from A to B and from B to C are two different material types, but the modulus of elasticity is both are given. Okay. So let's go through it. Before we go through it, let's think about what do we have to calculate. These are the two equations to answer the answer. Question 1, question A, ask for the stress. There, axial stress, axial force divided by area. Okay. The second question is about movement. Basically, how much it moves would relate to how much it shrink or expand. Therefore, that is the equation that we are looking at. We just derived it today. Okay. If we look at this, A, we know they give us cross-section area, rectangle, circle. We can calculate A. We can calculate N because they give us the forces. We are very good at equilibrium by now, so we can calculate N's. E, the Young modulus, the question also give them both. The length, they also give us. So there is no problem here. We can solve it straightforward. Okay. First, since at this moment in time, what we have to still calculate is N and the area. So let's go for it. The area. Two areas. Square. In fact, it's not rectangle, it's square. And a circle. This is how we calculate the areas. Okay, move on. The axial force. How do we calculate forces? I repeat myself, we use free body diagram before we set up any equation at all. Okay, so that is before point C, between point C, point B and point C. Okay, therefore it is called axial force between B and C, NBC. Simple equation. And then the other part between B, A and B. Okay, so we cut between A and B. This is the picture I see. So we can calculate NAB. We know that the axial force, the internal force, it is not really, we are not talking about left, right, up, down. Right? Axial force, we are actually talking about compression or tension. Okay? Notice that this type is a tension, pulling the material apart, meaning make it longer. This one, in fact, in all is a compression. Therefore, from A to B will be shrinking, will be shorter. Okay? So, now once we calculate N, remember that we can calculate sigma straight away. Okay? Which is the stress. Stress equal to the force, the axial force over the area. We calculate axial force, we calculate area, then we get the answer. There. Same, the stress for A to B, we know axial force, then we also use the axial force and the area to calculate the change in the length. Okay, so delta between B and C, as I said, since it's tension force, therefore this part become longer. Whatever we calculate then become extended. Okay, the axial force, the length, the Young modulus, the area. Right? So the second part, then A and B. Right? We know the axial force, we know the area, we can calculate the stress straight away. Then we can also calculate the delta, how much it change Again, the same equation. Axial force times the original length times the Young modulus, divided by Young modulus divided by the area. This one here, since NAB is in compression, therefore it becomes shorter than it was before. Now these are not the answer yet. If we read the question carefully, it asks for the movement of B and C. It doesn't ask how much it shrink or extend. It asks how much it moves. What is the movement? Okay. So let's look at the geometry here. Don't forget we know how much AB shrink and how much BC extend. Okay. How do we calculate it? Okay. Well, it is a comparison. Okay. Meaning the movement of point B will be relative to movement of point A as well as the shrinkage or extension between A and B. In this case, we can dictate that delta B is equal to delta A plus AB, delta AB. Okay? Delta A, the A doesn't move, right? A is on fixed support. Therefore, A does not move. A stays still. Therefore, delta A is equal to 0. Then, if delta A stays still, then AB becomes shorter, right? Therefore, B has to move towards A. B have to move towards A. Okay? Therefore, it can shrink. And the extension is equal to that one. So that is the movement of point B. What about point C then? Point C move not relative to A, well, in a sense it's relative to A, but in our calculation it's actually relative to B. Okay? So basically, before we talk about the extension or this B, this is C. Okay? Before we talk about the extension, we talk about how much it moves together first, and then C extend. Okay? So in essence, it means that delta C will equal to the movement of delta B first, and then combine the effect of shrinkage or extension between B and C later. So it expressed in this equation here. Okay? Put in the sign positive, negative. Okay? Now, we know that point B already moved to the left hand side, so it moved by 30 times 10 minus 3. Then BC extend, right? To extend, now point B already moved here. To be able to extend point C, point B doesn't move anymore. Point C actually move away from it. Okay? So basically, point C moved to the right hand side compared to point B. Therefore, that one is taking the effect. Then once you combine them, then it becomes positive. Because of the sign convention, we just said to the left hand side positive. So even though C move out this way, but compared to the original distance is probably here, it's still moving to the left by that amount of displacement. And that will be the answer of the movement of point B and point C. In the summation, there we go. We calculate the stress between A and B, stress between B and C. And then we also calculate the movement of point B, and we calculate the movement of point C. Then that complete all the 4 answers we need. Let's look at another example. Okay? That one there, well, it doesn't actually give us direct axial force idea. However, the key word is that this beam here is a rigid beam. The word rigid means it doesn't deform. It moves, but it doesn't deform. Okay? That one, the solid. The word solid means it can deform. So basically, imagine this. When you press the beam down, according to the mechanic, there will be reaction happening at point A and point B. Notice point B simulates the roller support, meaning only one reaction there. Okay? And then, but point D is a fixed one. Okay? There is also tau, the modulus of elasticity of the column. That one. So what we want to know here is what is the stress in column BD, that column there, and also the vertical movement of point B and point C. Okay? Let's see how we're going to have to go through it, shall we? Okay. the same equation apply. Apparently it gives us the cross-section area, right? So we can calculate the area. It gives us length, it gives us the Young modulus. So now what we got stuck with is the value of axial force. Okay, so let's go determine axial force. The free body diagram. Okay, that one there will be RB, that one will be connecting to the column BD, right? Action reaction. If column BD push the beam by RB, then the beam will push the column downwards, opposite, right? Equal to RB as well. So if we calculate that, take moment about point A, we get RB straight away, apply that to the column, and then find out the internal force, axial force for BD. There we are. Sigma Fy equals 0. Then we have the axial force acting inside BD. And of course, by the symbol, well, or even by sense, this one here is compression. Now, once we get N, then we need the cross-section area. It's a hollow cross-section area, right? So what we use is, in this case, what I do is I use the total block divided by the space, but divided by the hole, and that is the whole block, the whole circle, 1.5, 0.5, total 20 millimeters. Okay, and then that one is 1.5 centimeter, 15 millimeters. Okay, the area then millimeter square. Now, we know the force, we know the area, then we can find axial force, axial stress, right? Axial stress, axial force divided by area. That's the answer. Since the axial force is compression, axial stress follows suit, also compression. Next, the delta. Again, we have the axial force, we have the length, we have the Young modulus, we have the cross-section area. Substitute everything in, then we have the how much it becomes shorter. Okay, that is the shrinkage or extension. Now, the same idea. Remember, at point D is a fixed support, right? So it is the reference point, meaning it doesn't move, or if it moves, we can measure it because there is support there. Therefore, delta B will be again relative to delta D, sorry, D dog. But since it doesn't move, therefore we can conclude that B has to move down. But that's not it. That's not all the answer yet. Apparently the question asks for 3. 1, stress in BD. 2, delta in B, right? At B, delta of B, displacement of movement of point B, and it also wants movement of point C. Let's look at a picture. There. We answer stress in BD, we answer the movement of point B. What we haven't answered yet is what happened to point C, how much it moved, but there's no column there. How to calculate? Again, the key word is rigid beam, meaning it doesn't change, it doesn't deform. This one here start off a straight line. At point A cannot move. Point A is a pin support. Point A stays still. Therefore, but point B moves down. Therefore, point B moves down equal to delta B. This we actually calculate already. And if the column, if the beam is rigid, then it must remain a straight line. If it remains straight line, then it will look like this. If you notice, this is 2 triangles. One triangle is this triangle, from A to B and to there, right? The second triangle is from A to C to there. These 2 triangles are what we call similar triangle, and therefore we can calculate the movement of point C, which in this case I will call it delta C. Okay, let's see how it goes. Similar triangle. Therefore, delta B divided by the base. Then delta B, the base is 4. Delta C, the base is 5. So there we are. And then we can find out delta C. Once we find out delta C, we complete all. We complete all the answer we needed. And this is summary. Now, let's look at what we have done so far today. Oh, not yet. Let's have further reading first. There are certain parts of the explanation I left out, and I would like you to search for it, to look for it. Okay? There is something, it's called Saint-Venant principle. Okay? I think he's French, so maybe it is Saint-Venant principle. Okay? And I want you to read it up. Also, I want you to look further in the topic. This is very concerned with the axial stress and axial deformation. It is called thermal stress and thermal expansion. Okay? Actually, I would like to call this one here is only thermal expansion, but on books call it this way, so be it. Now, we're done. So let's summarize what we have done so far. We start off because we already discussed what stress and strain, and I hope by now you understand what it is. We discussed how we formulate it, how we actually look at deformation. Okay, so we create the formulation of the stress and deformation. Actually, we link it back to the axial force. Then we saw 2 examples. Then to enhance your understanding, and you need this enhancement, there are some further readings assigned. And this is it for today. Thank you very much. I hope you enjoy it, and I will see you again in the next lecture. Thank you.